Last class we started discussing the linearity of the mixer and the how to design the transconductor stage. So let us quickly review that. So we are discussing the Gilbert cell active mixer. So the reason it's called a Gilbert cell is because, as I mentioned several times earlier, it was used to, the same topology was used to build a multiplier circuit, and therefore we are pretty much using the same multiplier as a mixer. And as you can see, even if you have a perfect RF signal with no other harmonics at the input, because the LO has all its odd harmonics, the RF signal will get multiplied with and get translated in frequency to different frequencies. So the one we are interested in a receive mixer is the IF frequency, which is omega LO minus omega RF. If you have a single balance mixer, you can get components LO, 3LO, 5LO and so on. If you have a double balance mixer, you can actually get rid of those components. Apart from that, you also have the RF signal mixing with the 3 omega LO and 5 omega LO and so on to give you further mixing products, right? So if you really want to remove all of these in your output, you will have to put in a very nice filter. The good thing is, in a receive mixer it is not too difficult, because your omega IF is usually much smaller than omega LO and harmonics of omega LO. So this is usually not a very big problem. However, there are specific cases where this can be a problem. We have seen this, for example, if you look at an AM receiver, the IF signal is of the order of the RF signal and the LO signal, so it can become a problem. Then we started discussing the transconductors that we are going to design for use in this mixer. And we said, let us start off with a very simple common source transistor. Of course, it has a certain GM, so that acts as a transconductance. Unfortunately, you also have a GM3 which goes along with this GM, a third order component, which will lead to IAP3 problems. Now, you can also go in for a differential transconductor. Now the single-ended transconductor, if you have a long channel device, it may have a small third order component. If you have a purely square law device, it will have no third order component at all. However, if you have a differential transconductor, you are assured that you will always have a third order component. So if you take this transconductor, you need to understand first of all the bias point. The gate bias point can be easily defined, right? If you define the gate bias point and this current, the VGS of this transistor is defined and the VDSAT for this current source is defined. If you have a common source transistor like this, you can similarly define the bias at the gate, right, using a current mirror. So you will have a pseudo differential or a single-ended configuration. Even if you want a differential configuration, we also looked at the pseudo differential case, where you can have two of these with plus VRF by 2 and minus VRF by 2. Now, if you want to define the operating point of this device very well, on top of this device, on top of the transconductor device, you have the mixing device. So to understand the VDS of this, obviously the GM3 is defined at a particular VDS. If you change your VDS, your GM3 component will change. So you need to understand what the operating point is. So we started looking at the behavior of the switching pattern. And what we said is, if you have an ideal LO signal, 0 rise time, 0 fall time, and the switches switch instantaneously, then this node will always be at what value? It will be at VDD minus VGS23. The common source node of the LO devices will be at 1 VGS or the VGS of 2 and 3 below VDD, because the input we are assuming is switching from 0 to VDD. If it was switching from 0 to V0, it will be at V0 minus VGS23. If these devices do not switch instantaneously, or if the LO signals have a finite rise and fall time, what you will find is, you will find that reflected on the signal at the common source point. This you would have seen in many different kinds of any differential circuit. You will see this, where the even harmonics of the signal will end up here. Because why does that happen? Every time the device M2 turns on and M3 turns off, or vice versa, you will see this node getting affected at the rise time and the fall time instant. So you will definitely see a very large second harmonic signal there. You will also see other fourth harmonic and sixth harmonic and so on, which will usually be much smaller. So what you want from this, you want very small rise time and fall time. You want, of course, very good symmetry. If you have a large LO amplitude, you will definitely ensure full current steering. You will also ensure that when we say large, we mean it should be much larger than root 2 times VGS minus VT. And when it is much larger, you will also ensure that the devices switch much faster, because the overdrive, the drive for the devices over their VD sat is much larger. So if you want the transconductor to be well behaved, you don't want very large glitches at its drain, you will definitely want a large LO amplitude. And we also discussed what happens if the amplitude is smaller than root 2 times VGS minus VT. Your conversion gain will get impacted, right? If the devices don't switch completely, then your conversion gain will be much smaller than what you can have with full switching. You can also improve the transconductance of this common source transistor by adding, for example, a resistive degeneration. And obviously the problems with resistive degeneration are you need to have a portion of the headroom devoted for this resistance, DC headroom. This resistor produces noise, so the noise figure of the mixer gets worse. But apart from that, linearity will look quite good. Now we wanted to see if this is possible without the use of a resistor. So next we went ahead and said, okay, so if you don't use a resistor, what happens if you put an inductance, right? And it turns out you can get some good linearization using the inductor. Problem is you are using up more area, but the good things are it doesn't use a lot of headroom. It doesn't produce any extra noise, not much more extra noise. And the other thing is it actually produces a second order system along with the CGS of the transistor. The second type of transconductor we looked at was the common gate transistor with a source resistance that you add. So the nice thing about this we found is that it's a very, very wide band transconductor. As long as you choose the appropriate value of RS and GM, you can get a very linear transconductance with a first order behavior. Now, as an aside, we also said that if you have a common source or a common gate transconductance and you are worried about specific harmonics, you can use some kind of harmonic filtering to actually get rid of these harmonics. It will not be, right? Because the RS signal will be equal to the LO signal. The signal you are interested in is at baseband. If you have a second harmonic signal, it will actually get mixed with the LO signal and come down to the RF frequency, which you can filter out very easily. Okay, so you are not interested in the second harmonic. However, the last circuit we saw was what is called a multi-Tannhäuser transconductor. So the basic idea is to increase the dynamic range of the transconductance, right? That is, normally what happens is when the amplitude becomes larger than a particular point, the GM starts changing from what you expect it to be, and that causes nonlinearity or loss in gain. So now what you want to do is you want to increase, even with a larger signal, you want to have the same GM, larger input amplitude signal. So one way to do that is to use different differential transconductors biased at different points. This is an example of such a system where you have the first differential pair which has a 1:1 ratio, the second differential pair has 1:A, and the third one has A:1. Now, depending on the values of A, you will get three different curves. Obviously, the zero crossing point will now be different because of the asymmetric ratio. So the symmetric one will pass through the origin, the asymmetric one 2 and 3 will go on either side. Now to find out the overall transconductance, you need to take the slope of this curve. The one which passes through the origin will have a GM curve like this, 2 will have a GM curve like this, 3 will have a GM curve like this, right? So finally what we do is we connect all of these inputs together and connect all the outputs together. So what is the overall GM? The overall GM is just the sum of these individual GMs. Your overall GM will look something like this, more or less. You will have to be careful in how you bias these. If I change the DC current, can I change these things? Let us say I change this DC current. Will it shift the point zero crossing? It won't, right? If you change the DC current, you can't, as long as the system is symmetric, you cannot. But what else can you do? The gate voltages of the transconductors, the bias points, the gate bias can be changed to affect the same asymmetry. Of course, the most important one is the transconductance nonlinearity. So you have VDC plus DRF at the gate. I out has a DC component plus GM not VRF, rather GM1 VRF, GM2 VRF squared, and so on. If you want to improve IIP3, apart from the circuit techniques we talked about, what else can you do? What do you need to do to improve IIP3? So yeah, you can use the resistive degeneration, inductive degeneration and so on. But is there fundamentally for the transistor, what can you do? The nonlinearity depends on the bias point of the transistor, right? Primarily on the VGS minus VT. Okay, so normally we have seen that something like this, let us say. This is GM3, right? It will look something like this. For normal regions, let us say you are operating here, right? Obviously, eventually as you keep increasing the overdrive, the nonlinearity will get better. So you ideally want to be operating in this region, somewhere close to this point. Why is that? Why not here? So why not here? Huh? GM1 will be very small, right? If you make VGS minus VT very small, GM1 will also be very small. Remember, GM1 looks something like this. Okay, so you don't want to be operating at this end of the curve. You want to be operating somewhere here. Okay, so that is why I said you want to be operating somewhere here. So normally you want to increase VGS minus VT. Now at a particular current, let us say your current consumption was fixed. How would you increase VGS minus VT? By decreasing the transistor size. That is the only way to do it. So if you do this, at fixed IDC, what happens to the GM? it has to fall. So in other words, this is a particular curve for a particular width and length of the transistor. Now you are going to a different curve for a different length. But GM will definitely fall. And obviously if GM falls, the conversion gain will fall. And if conversion gain falls, what happens to the noise figure? Noise figure will get worse. Okay, so this is a fundamental problem you have to worry about. If you are trying to make the transconductance more linear by changing the overdrive at a fixed DC current, then this can happen. Obviously, if you have control over the DC current, then you can try to compensate for this. So the next step is, do the LO switches cause any nonlinearity? They are just jumping from on to off. Are you using them as resistors? No, you are not. Not in this kind of mixer, right? So it's going from on to off, but they are going from saturation to cutoff, not from triode to cutoff. Okay, so when they are on, they are acting as cascode devices. Do you expect any nonlinearity problems from the cascode? Normally. Not a major problem, right? Normally you expect the nonlinearity to be limited by the input device, right? The cascode just acts to shield the input device from your output node. So even though your output node is swinging, the main device normally has a, so if I have a cascode like this, and this is Vn, so this is my output node. My output node may be swinging, but remember, this node doesn't swing a lot. So in fact, the cascode actually helps with nonlinearity. It actually shields your transconductor from the output swing, as long as the cascode is in the saturation region. So if you look at the LO switch, as long as the LO switch is in saturation, it seems like it is going to shield your transconductance. Now there is one caveat. Remember that if you take a single balanced mixer as an example, if you look at this node, you have the second harmonic signal coming here. You need to make sure that component is small enough such that it doesn't disturb the operating point of the transconductance. So that is one point. Apart from this, can you think of any other issue with this, with the LO switch nonlinearity? So if there was a cap here, let us say Cp, there is a parasitic capacitance, right? There is a lot of parasitic capacitance because there are two gate source capacitances of the LO devices and the drain bulk and drain gate capacitance of the RF device and the source bulk capacitances of the LO devices also. So there could be a large capacitance at that node. Okay? If this capacitance is large enough, what could happen? Earlier at this node, to make sure that KCL is valid, right? The two currents, the current through the LO device has to be equal to the sum of the currents through the LO devices has to be equal to the current going through the RF device, right? What is the current through the RF device? Assuming you have an ideal transconductor, it is just going to be the DC current plus the signal portion, right? So the current flowing through the output is also constrained to be equal to these two, except multiplied with an LO signal, right? Multiplied with S of t. However, if you add a third path for current to flow through, if you have a parasitic capacitance Cp there, what happens is you now have a third path for current to flow through. And what does that current depend on? It depends on the voltage amplitude here. Okay, it is related to the voltage amplitude. If you look at the output current, obviously it is no longer going to have only the signal plus RF. You are definitely going to see a reduced gain. Apart from that, what kind of nonlinearity can you see? Even order nonlinearity. Why is that? Because the voltage over there has an even order component. Remember, the voltage there is still, because it's a differential node, it's still constrained to have only the common mode component, not the differential mode component. Therefore, the current through that will also have the even order component. So this can lead to even order nonlinearity, not odd order nonlinearity. Is that clear? Okay. So this is as far as this parasitic capacitance goes. Now, suppose I look at just the gate source capacitance of the LO devices. So I'll call these two devices M1 and M2, and the currents through them I1 and I2 in this direction. Let's say this was node X, and what I'm going to say is the LO plus node is rising from 0 to V0. And the LO minus node is experiencing a falling edge. This is your tail current. So what is happening? M1 has just turned on, right? And M2 has just turned off. So this is the state immediately after the transition. What is the capacitance at this node? CGS1. What is the capacitance of device M1? 2/3 WL Cox. Right? Let's say this was CGS2. What is CGS2? No. It will only be the overlap capacitance. The other capacitance with respect to bulk. Okay. The capacitance with respect to bulk is a fixed capacitance. So whereas here we are interested in the gate source capacitance specifically, as you will soon see, because the gate node is experiencing a transition. That is why we are interested in this capacitance. I'll call this the overlap, I'll call it LD, which is the overlap capacitance. Now, because these two capacitances are different, I'm going to call these currents through this IP1, IP2. Because these capacitances exist, they are going to have some amount of signal current through them. And unfortunately, because CGS1 is not equal to CGS2, those two currents will not be equal. We are still interested in KCL at node X. We are still interested in KCL at node X. So, the current flowing into the node is I1 plus IP1. The current flowing out of that node is I2 plus IP2 plus I tail. So let me just call that IP. Okay. So I1 is nothing but I2 plus. Actually, what is the value of I2? I2 is 0 because the device is just turned off. I2 is 0. So I1 is nothing but IT plus IP1 minus, IP2 minus IP1. In the time domain, they are going to be related to the, if you are writing these currents in the time domain, they are going to be related to the voltage across the capacitor. Now we will also make another approximation to make things easier for us. We will say that the current through CGS2 is very small because the overlap capacitance is very small. So we will say that this is approximately equal to IT minus IP1 because IP1 is much larger than IP2. What is this? D by dt of VLO minus Vx, right? That is the VGS of the transistor, the voltage across the gate source capacitance. So this is what is called the displacement current, because you have a capacitance with its voltage changing across it. So you have a displacement current flowing through this capacitance. So why does this cause a problem with linearity? So we have neglected IP2 and I2 is definitely 0 because the device is off. So there is very little current flowing through this portion, right? So we can ignore it. We are interested in the current in this portion. So what you had as a linear current IT is now getting split through CGS1 and M1, right? So what should have flowed completely through M1 is now part of it is getting diverted through CGS1. If the part that is diverted becomes large enough, what can happen to M1? It will go out of saturation, right? If the current becomes small enough, the device M1 which you wanted to be in saturation can go into linear region. So if I1 M1 and I'll say M2 on the other half cycle, may leave the saturation. Obviously, this will lead to nonlinearity. How can you keep this displacement current low, or what can cause it to become high? The d by dt of the LO. At the end of the day, Vx is, the change in Vx is very small. It is actually d by dt of LO that causes all of this displacement current. And in other words, if dLO by dt is large, okay, that is, so in other words, has sharp edges, so this makes it more nonlinear. Okay, so in other words, if you have very sharp LO edges, this will actually make this nonlinearity worse. So remember, we started off saying you want these devices to switch immediately. But that was the case when you had ideal switches and you wanted zero rise time, fall time. So you had a perfect SFT. Now when you start looking at the nonlinearity of these devices, when you look at real devices which don't switch instantaneously, which have parasitic capacitance associated with them, then you find that you cannot have infinitely large, rather infinitely small rise times and fall times. Apart from this, the other component we looked at if you look at the component of CP, so if you want faster switching, right, what we said was this directly relates to the lower overdrive, but the minute you want lower overdrive, you will need to either increase W23, okay, which means, why do we want faster switching? If you have slower switching, this node X that we talked about swings a lot more. Anything else? What happens to your conversion gain? If you have slower switching, there is a larger and larger region where both M2 and M3 are on at the same time. You will directly see this as an impact on conversion gain. Obviously, the impact on conversion gain will happen when these rise times and fall times become much larger. But if you want to achieve this lower V overdrive, obviously this parasitic capacitance can increase, which will reduce the conversion gain further. The other option is to decrease the DC current. So which means again GM23 reduces and again your conversion gain reduces because you have lesser current going through this compared to parasitic capacitance. If you have a very smooth sinusoidal with same amplitude, you are talking about a sinusoid of the same amplitude with 2 by pi of the square wave. So let us say the square wave was V0, you want to have 2 by pi V0, a sine wave with 2 by pi V0. Okay, so let us assume that happens. So let us say this is the point where the square wave is switching, right? If you look at the sine wave switching, it looks like this, right? What happens to M2, M3? How much time do they turn on? Are they on together for the same time? It depends on root 2 times VGS minus VT. So there is actually a much larger window around this where both are on. You will again see a decrease in conversion gain, even with a sinusoid. Now, obviously, it depends on what V0 is. Okay, if V0 is much larger than root 2 times VGS minus VT, the portion for which they are on will become much smaller. You will not see a huge impact. So let us start off looking at noise in Gilbert cell mixers. So we have looked at conversion gain, we have looked at the basic operations, single balance, double balance and so on. And we have looked at the nonlinearity. What are the sources of nonlinearity? So primarily from the transconductance device, but because of parasitic capacitances, the LO devices can cause nonlinearity also. So finally we come down to noise of Gilbert cell mixers. So what are the different sources of noise? Obviously you can have noise from the transconductance, noise from the LO devices and noise from the load. We will start, doing it in a certain order because analysis is easy for the transconductor and the load. So let us start off with load noise. So let us say you had some load resistor RL. So it is purely resistive. The output voltage due to the resistor is nothing but 8 kT RL. Why is it 8 kT RL? Because you have two RLs. So my assumption is this is my mixer core. These are the two RLs. So the total noise due to these two resistors is 8 kT RL. What about flicker noise? Can you have flicker noise? Normally no. Normally from a resistor. But of course you should be careful about the kind of resistor that you use and make sure that the flicker noise is very small. What are the issues with this resistor? Obviously, if you use a resistor, your voltage headroom has a direct relationship with the DC current. The output common mode is nothing but VDD minus IDC RL, and you don't have independent control over this because RL affects both the output common mode and the conversion gain. The DC current affects both the transconductance as well as the output common mode. Okay? As I said, conversion gain is proportional to RL. You don't have independent control over all three parameters. What can you do to fix this problem? You can use some kind of active load that will help you set the output common mode and break this connection between the headroom and the gain, conversion gain. This is the mixer core. This is VDD. I'm going to do something like this. What is VOCM? Is VDD minus VGSP. What is the conversion gain? Depend on. Earlier conversion gain was proportional to RL. What does conversion gain depend on right now? RB and GDSP. Okay? If you don't want to give enough headroom equal to VGSP, so if VDD becomes very small, you want to have even better headroom, you need to give some kind of common mode feedback. So I'm going to take this guy. I can do this, and very possibly I might need some compensation for that loop. But I can set the output common mode independently. So in this case, VOCM can be set to VDD minus VD sat P. So of course this circuit can give you the best possible headroom. So you can have some kind of Miller compensation cap to stabilize the loop. What kind of noise can you expect from here? Obviously noise from the PMOS devices. So this can be 1 over F noise and thermal noise. If you are operating with low IF or direct conversion receivers, 1 over F noise is a problem. Thermal noise could always be a problem. So of course this means this 1 over F noise problem means you might need to use very large devices.